Hi everybody. In the last video, I talked about how if we're trying to solve an equation and we end up with a nonsense statement like 2 is equal to 6 or 3 is equal to 5, which of course is nonsense, then that means that the equation which we were trying to solve in fact has no solution. There's no number that we can put in for x or b or d or whatever it is that makes both sides of the equation the same. But I didn't explain why that is the case. And that's what I'm going to try to do in this video. So I want to answer the question, why is it that if we get a nonsense statement like 3 is equal to 5, then the equation has no solution? Now, in order to answer that question, we have to talk a little bit about logic. So this is something that I want you to understand, and I'll give you an example, and hopefully it won't be too hard to understand. If you have a statement such as if P then Q, and you know Q is false, then P must be false also. That might sound a little bit strange, but I promise you it'll make sense once I read the following example. So in this statement here, this is my P, okay, and this is my Q. So here's my if-then statement. If Mr. Friedman jumped into a swimming pool, then Mr. Friedman is wet. Okay, makes sense. But now let's ask ourselves, is this part of it, if you look at me right now, is this proposition that Mr. Friedman is wet, is that true or is that false? Take a good look. Am I wet or not? No, I'm not wet. I don't think I am. I think I'm perfectly dry. So this proposition over here is actually false. And if this is false, if my Q over here is false, then my P, which by the way, the P is called the antecedent and the Q is called the consequent. If my consequent is false, then my antecedent must also be false. So if you look at me and you see that I'm not wet, then I must not have been jumping into any swimming pools lately, which kind of makes sense, right? So if I have a statement, if P then Q, then if I know that Q is not true, then P must also not be true. If Mr. Friedman jumped into a swimming pool, then Mr. Friedman is wet. Okay, fine. But if I see that Mr. Friedman is not wet, then that means that he must not have jumped into any swimming pools. Okay? All right, so what does this have to do with math? Well, if we take a look at, let me go back to a couple of the equations that we actually looked at in the last video. This equation actually had a solution, x minus 11 minus x is equal to 4. But now let's look at it through the lens of logic. Now, something which maybe you haven't thought of before, but it's really good to know, is that when you go through the process of solving an equation, when you perform inverse operations on both sides, or you distribute, or you combine like terms, or you do whatever it is that you're doing in order to solve the equation, and you keep writing new lines of the equation. So we started with this equation, and then we subtracted 11 from both sides, and then we got this, and then we divided both sides by 1, and we got this. What we're really doing is we're creating a series of if-then statements. We're saying, if this is true, if 11 minus x is equal to 4, then this must also be true. And then after we divide both sides by 1 here, then we're making another if-then statement. We're saying, if this is true, then this must also be true. So in this example, this is my antecedent over here, and this would be my final consequent. So if there is a number such that 11 minus that number is equal to 4, then it must also be true that that number is equal to 7. That's the if-then statement, which we're really making, or really we broke it into two if-then statements. If this is true, then this is true, and if this is true, then this is true. Or you could think of it as just going from here to here. If this is true, then this must also be true. So x is equal to 7, that's perfectly fine. Okay, no problems there. But what about the first example that I gave you in the other video that turned out to have no solutions? Let's see what's going on there. In this, so this was the equation that I gave you in that video. And now let's think about it logically. What we're saying is, so we started with this equation and we subtracted x from both sides, and then we got 2 is equal to 6. So what are we saying here logically? We're saying if there is a number such that that number plus 2 is equal to that number plus 6, then it must also be true that 2 is equal to 6. But wait a minute, 2 is not equal to 6. So we get this situation just like we got back up here, where our consequent is false. And if our consequent is false, then our antecedent must be false also. Here, if you look at me and you see that I'm not wet, then it must also be the case that I didn't jump into any swimming pools. Down here, if you see that we get a nonsense statement, so you see that 2 is not equal to 6, this is false, then it must also be the case that this antecedent is also false. So there is no number such that that number plus 2 is equal to that number plus 6. Okay, so everything that I said in the last video, if you get a nonsense statement, then it means you have no solutions. That follows from the laws of logic here, okay? And by the way, this would be called the contrapositive. If I have an if P then Q statement, then the contrapositive would be if not Q, then not P. So I'll just throw a little vocabulary in there at the end. So anyway, I hope that made sense, and have a great day.